zeolite growth. You can show that this is a real, it has something to do with zeolites because it is very acidic. You can do a hydrogen exchange, you can make, you can put ammonia on and you see the ammonium formed with infrared and so forth. So we believe that we can really start to do some studies that may help some phenomena to be understood. I mean, I'm completely aware of the fact that this is not a real zeolite, but you have to realize that thin film of silica is only van der Waals bound to the metal underneath. It's a large distance. Actually, molecules can creep in. You can also do interesting chemistry there in that little hole, but it's not very much affected by the metal. So we can perhaps do that. But there is another phenomenon that is perhaps even, well, I shouldn't say more interesting, because what could be more interesting than zeolites? But there is an interesting phenomenon that has to do with the structure of the silica film. And that brings back my physics background a bit. You see, here's the crystalline structure. It's almost perfect. You see these hexagonal rings. And then Marcus Heide came with this image to me. And I said, what is this? You know, that looks to me like a glass. If you look in reciprocal space with electron scattering, it is like an amorphous solid. Now, I have been trained in my physical chemistry courses that the glass crystal transition is still not understood. And there are certain aspects that are very well understood, but when you look at the structure in real space, it hasn't been done. And we've been looking at this in the literature. And in fact, there is a paper by William Zachariasen, from 1932. And because the editor of JACS at the time could not allow three-dimensional structures to be drawn, he invented an image of silica that looks like this. He just took a silicon and 3 oxygen atoms and made it planar. And he said what we have is a network of different ring sizes. So when I remembered that, and I said, has that been proven? We looked it up, and there are many, many pictures that I could show you until about 2-3 years ago, where people have made attempts to see the atomic resolution on a glass. Never been proven. But the Zachariasen model has been used all the time. So I asked Marcus Heide, who is the instrument builder, to look at that more closely. And that's the first image he got, which with better resolution. That's already pretty close, isn't it? But it's not the direct proof, because if you want to have a direct proof, you would have to be able to show this is silicon, this is oxygen. And the 4th oxygen goes into the plane, right? You understand that? And at the same time, I was, and I have been in the past for many years, interacting with Joachim Sauer in Berlin, and he's sort of my reference for zeolites and for silicates. And he looked at that and said, yeah, let's see what we can do. In fact, he was already involved in the structure. Without the calculations, we would not have been able to really pinpoint the structure that much and interpret the infrared spectrum. So that was a very crucial, very important ingredient. But they started to look at this as well. But at that time, Marcus made a convincing, to me anyway, a convincing image. And that image comes about because the SDM that we have has the ability to do non-contact AFM and SDM on the same spot. So you can sit on an atom and change from SDM to AFM. And that changes the contrast, right? AFM has a different contrast than SDM. And SDM gives the oxygen contrast, and AFM gives the silicon contrast. So you take an image, and you see it here. This is the non-contact AFM, and you see here's the oxygen contrast, the silicon contrast. And you see the same image, the same area. You see this identical area here. And this is the oxygen contrast. You could put the two on top of each other, and you've proven the Zachariasen model. Now the question is, and that's what we're working on, can we look at the dynamics? Can we see how the ring sizes change and how all that arranges in the process? So we have just received the funds to build a new SDM that allows you to do that between 100 Kelvin and 1,000 Kelvin. So that's that way. That is, I think, a very interesting topic. And of course, this can also be used to do models in catalysis. We can, for example, look at the ring distributions. And if we can put hydroxyl groups onto this and anchor atoms to it, we can get models that way we can do single-site catalysis. That's something we're also working on. Here, by the way, just to prove to you that this is a glass, if we take the SDM image and Fourier transform it and make a pair distribution function out of it, that's what the people with X-ray scattering and neutron scattering always do, and you compare them. This is the SDM, taking the sensitivity into account. Neutrons have different sensitivity than X-rays. You can see a pretty good match in it. So it's actually a piece of glass. You can also look at interface already between the crystal and the glass. You see, here's the crystal, here's the glass, and you can ask the question, how wide is that interface between an amorphous and a crystalline solid? And Leo Lichtenstein did an analysis where he defined the so-called crystallinity factor. He didn't define that, that is defined. And this crystallinity factor is 1 as long as you're in the crystal, and it goes to a certain, what they call vitreous average when you are fully in the amorphous phase. And you can see, if you do that for that interface, you can actually see it takes about 2 nanometers to go from a crystalline to an amorphous phase. That's the spatial arrangement you need to be able to do that. And if we can now start to look at the dynamics, that would be interesting. But we have been able to make hydroxyls on the surface. This is infrared. We're still working on the interpretation of it, but we have been working on it for a while because you cannot just put water on it, even if you put water at high, whatever, exposure on it, a drop of water. It doesn't work. You have to use electrons to induce it. And if you do that, you have to be really careful that you're not destroying the structure. But you can actually do that. So I think we're on a good way to actually use these silica films as models. And what I would like to see, I'd like to put a chromium atom, put ethylene, and see the chain growth on the surface. And I believe that the toxicity problem of polymers are not, that the surface helps a lot to do that. And people tell I'm crazy, but I think it's interesting to look at. And that's what we do next. So, again, a lot of support from theory, and I would like to say in closing that this interaction between theory and experiment is a crucial one. And we, the experimentalists, need the theorists, but the theorists also need the experimentalists, and that sometimes, I have the feeling, is forgotten. When I hear some of the talks in this conference, I have the feeling some parts of theory think that experiments are not needed anymore. I'm not sure that that's true. So on that note, I would like to close. I hope I've shown you that these films, by being pretty and neat to look at, could be useful. We can look at electron transfer, we can look at elementary processes, and we even have now the chance to look into something I never dreamed we'll be able to do. Perhaps we can contribute towards zeolite chemistry, and perhaps we can solve a long-standing problem concerning the glass crystal transition. It is very clear that none of what I told you today is my work. This is all the work of the many students and the postdocs. This is a photo of the group, and you can see we have a yearly meeting, and my friend Gianfranco, who is a theorist, who could not stay until the day of the picture, was photoshopped in, and you can see that. It's not very well done, but it is. When I saw this picture the first time, I thought even Ahanu is okay, but I thought Joachim Sauer was photoshopped in. I don't know where he is now. I can't see him from here. Joachim Paya would probably identify it from back there, but he's not photoshopped in, he was there. So we have this collaboration with many groups outside. I am particularly grateful to the Alexander von Humboldt Foundation for funding many Humboldt awardees in Germany, among them the president of the society. In particular, I would like to thank my collaborators. Some of them are mentioned here. We have a group of consultants. We call them post-profs. Those people who are retired in Germany can spend some time, at least at the Fritz Haber Institute, after retirement. And you cannot imagine how important it is for the young people to be able to talk to these very experienced people in the field. So I'm more than grateful to all of these people. They have done the work. I'm only the clown presenting it. And thank you very much for your attention.